In this video, we shall treat a question on method of moments. We are asked to estimate the mean and the variance using the method of moment from the given uniform distribution. Solution. For more on this topic, you need to subscribe to this channel. The first thing to note that for uniform distribution, we have that it is bounded by a plus b all over 2 and b minus a all squared all over 12. So for uniform distribution, so it then means that our expected value of x is equal to this, and our variance of x is what we have here. So, and for the method of moment, for we to get our answer for the method of moment, it means the population mean must be equal to the sample mean. That means we move over to here. For the first moment, we have that mu is equal to this. That means the population mean must be equal to the sample mean for we to have our moments. And the population mean is equal to the expected value of x. That means what we have here, the expected value of x. Why the sample mean is equal to 1 all over n summation of xi as I running from 1 to n. So this is our sample mean. Of course, you know what this thing is. This is mean. So how do we obtain the population mean? The population mean, like we have here, is equal to a plus b all over 2. So we have to work on this. It then means that our population mean is equal to the expected value of x and is equal to what is a? A is this. They are bounded. This is a and this is b. So we have mu minus the square root of 3 sigma square plus b. We have b to be mu plus the square root of 3 sigma square all over 2. So of course, this can cancel this. So we have this to cancel this. And we'll be left with mu plus mu all over 2, which is the same thing as 2 mu all over 2, which is the same thing as mu. So it then means that mu 1 is equal to the expected value of x, which is equal to mu. Why n is 1 all over n summation of as I running from 1 to n xi. We know this thing as our mean. So we can call this equation 1 and we call this equation 2. So our method of moment is just to compare the population mean and the sample mean. So we'll move over to this side of the board. We'll move over to this side of the board. Since we've gotten our population mean and our sample mean, we'll now write it out here properly. For more on this topic, you need to subscribe to this channel. So we say comparing equation 1 and equation 2. If we compare them, we now have that our population mean is equal to our sample mean, and it then means that our mean is equal to x bar. So this becomes the first moment. Now, for the second moment, we succeeded in obtaining our mean. For the second moment, we have our population mean to be equal to our sample mean. Also, our population mean is equal to the expected value of x squared, and our sample mean is equal to 1 all over n, as I running from 1 to n, x squared to be our sample mean. Now, how do we obtain the expected value of x squared? How do we obtain the expected value of x squared? We'll move over to this side of the board to show that how we can obtain the expected value of x squared. For more on this topic, you need to subscribe to this channel. So how do we obtain our expected value of x? We should recall that the variance of x is equal to the expected value of x squared minus the expected value of x all squared. So if we make this the subject, that is the expected value of x squared, which is the same thing as this, will be equal to the variance of x plus the expected value of x all squared. So this is what we get. It then means that our population mean for the second moment is equal to the expected value of x squared to be equal to our variance. We have our variance, like what we wrote before, to be b minus a all squared all over 12. It will now be plus our expected value of x all squared. Now, our second moment for the population mean, which is equal to the expected value of x squared, will equal to b minus a. What is b from our equation? Our b is mu plus square root of 3 sigma squared, and our a minus A, which is mu minus, because of this sign, half plus square root of 3 sigma squared as well, bracket, all over 12, minus what we have here, our expected value of x, what we got, our expected value of x, we got it as mu. We got it as mu. Our expected value of x, we got it to be mu. So we got it to be mu all squared. Now, it then means that our population mean for the second moment, which is also equal to this, is equal to, now, if you open this, you will see that, okay, let me write it out. Mu plus square root of 3 sigma squared minus mu plus square root of 3 sigma squared all over 12 minus mu squared. So this will cancel this. Now we have this plus this, sorry, all squared. Now we have it to be root 3 sigma squared plus root 3 sigma squared all over 1 all over 2 minus mu squared, which is the same thing as, that means our mu, which is equal to the expected value of x squared, is equal to this plus this, we get 2 sigma 3, no, 2 square root 3 sigma squared all squared all over 12 minus mu squared. So this is what we get. Now we'll have to open this, which is the same thing as 4 multiplied by 3 sigma squared all over 12 minus mu squared. So this is what we get. We'll move over to this other side so that we can obtain the population mean for the second moment. So we'll move over to this side, but we should note that our mean for the first moment is equal to x bar. Now we have our same population mean for the second moment to be, we have 12 sigma squared all over 12 minus mu squared, which is this. 4 times 3 is 12, which is the same thing as this will cancel this. So we'll be left with, okay, this is plus this, plus this, plus this, and plus this. So we have sigma squared plus mu squared. So it then means that our population mean for the second moment will give us sigma squared plus mu squared. So this is what we'll get, because from here we have variance plus this, variance plus this, variance plus this. So it will be variance plus this, and the whole of this plus this plus mu squared plus mu squared. And we have it as this plus this plus this. So our population mean for the second moment is this. Now, what is our sample mean? Our sample mean is 1 all over n summation of xi squared, like we wrote before. So this becomes our, say, equation 3, and this becomes our equation 4. Yes. So comparing equation 3 and equation 4 together, we have mu 1, 2 to be equal to our sample mean 1, 2. So it then means that this, which is summation, sigma squared plus mu squared to be equal to 1 all over n summation of xi squared as I running from 1 to n. Of course, we should note that we move over to this other side of the board. So we are not done computing the variance. We'll move over to this side of the board to compute the variance. For more on this topic, you need to subscribe to this channel. All right. Now we should note that we got this to be equal to this for our first moment. So it then means that mu squared will be equal to x bar squared. Meaning if we have sigma squared plus mu squared equal to 1 all over n summation of x I squared as I running from 1 to n, we can write this to be equal to x bar squared to be equal to 1 all over n summation of xi squared. Of course, this can move over to this other side to give us sigma squared to be equal to 1 all over n summation of xi squared minus x bar squared, which is the same thing as summation of xi minus x bar all squared all over n. Nothing has changed. So it then means we have our sigma squared to be summation of, as I running from 1 to n, xi minus x bar all squared all over n. Now, if we take the square root of both sides, we'll now have our sigma to be equal to the square root of sigma from I running from 1 to n, xi minus x bar all squared all over n. So this is what we have. This is what we have. as our sigma for second moment. Of course, we are asked to find the mean and the variance. Of course, this is the answer for the method of moment for the given interval. The second moment, why this is the first moment for the given interval. So this is how we can compute the method of moment estimation when a uniform distribution of a given interval is given.